record it now. Okay. So this is the last chapter. This is the last chapter in Code Algebra. In this chapter, we are going to study two new functions. Que es transcendental function. Transcendental means que es beyond the polynomial and rational function we studied before. Transcendental. We start studying this function in the Code Algebra, and if you take pre-calculus or trigonometric, you continue another transcendental function. Okay. The name of this transcendental function is exponential and logarithmic function. But today, maybe we have no time to cover this. This is just introduction to the first part. And this is important, guys. Not exactly today. Not exactly maybe next week. Next week, yes. We need to use a calculator. Calculator. Scientific calculator. Okay? Because that functions, exponential and logarithm, we cannot compute it by hand. It's impossible by hand. We need calculator, okay? In the test, we can use a calculator because you need to compute that functions. Okay, so let me recall something that you know, but I want to refresh your memory. It's about definition for the function. And what is one-to-one function, and what is the new idea against inversive function. So basically, in that part, we recall quickly, of course, the idea behind one-to-one function. And the new idea is inversive function. This is new, completely new. Okay, suppose the schematic diagram que represent domain and range, exactly the same way I do in the chapter 2. And so now we have, for example, the classical one-to-one relation in which one value of the x is associated only one value of the y. This is a function, of course. Pass. Many to one is when the two value, for example, of the domain is assigned and one value, yeah, two or more than two to one value. This is many to one. Many to one is also a function. But one to many is one value of the domain is associated with two value of the range, no function. So that part is not okay. It's a contradiction with the definition of the function. Okay, I understand. However, what's the problem today? The problem today is inversive function. Inversive function. What is inversive function? Well, inversive function is the function but in opposite direction, like that. That is a reason that it's inverse, no? In that direction. Well, there are many examples of the inversive function. For example, one function easy, elementary, x plus 10. The inversive function is x minus 10. Because subtraction is the inverse operation of the addition. Suppose another function is x over 2 divided by 2, and 2x is the inverse function. It's inverse function. This is the idea behind. For example, x squared and a square root is inverse function because on those each other. Let me show you. Let me show you the idea. The inverse function. Look, suppose you pick one value, 5. And you square 5 squared is 25. And you find the square root of 25 is 5 again. Okay, wow, we come back at the beginning. Okay, and always happen when you addition 10 and subtracting 10 and you put together the combination, it's obvious that you are doing nothing. This is nothing. This is x and this is also x. Okay, this is the idea of the inversive function, and this is important. Why is important? Because the function that we study, exponential and logarithmic, not today, they are inversive function. So this is important concept to understand the relationship between this kind of special function we study in the chapter. Exponential and logarithmic are inverse function. Now, it's important to understand one more thing. This is very important moment now. The notation that we are using to denote the inverse function is something like that, f negative 1. But this f negative 1 is just symbolic way. Symbolic way to indicate inverse function. This is the inverse function. So this thing que es symbolic, que look like negative 1 exponent, actually is not negative 1 exponent. No. So this is not this reciprocal. No. This is a symbolic way to indicate inverse function. Okay, this is the most important concept. But it's obvious que, bueno, wait, we have inverse function here because it's exactly the same but in opposite direction. Pero here, no inverse function. So the inverse function here, the inverse function do not exist. Why do not exist? Because in this opposite direction, my relation become like a one-to-many. Look, one-to-many. When I inverted I put the opposite reverse arrow is one-to-many, and one-to-many is no function. Wow. So to exist the inverse function, the most important requirement is that my function would be one-to-one. So it's if you want that the inverse function exists, the first requirement is that the original function, original f, is one-to-one. Otherwise, no. So it's not one-to-one. You see in this example, no inverse. And here is no function, no? So the only thing is in one-to-one. One-to-one function is the only, possibility to be invertible. The function invertible. So in other words, the inverse function exists. Okay, no problem. Let me erase in this way. Okay, boom. Okay, I understand. But how do you know? Well, in this case, it's easy because you see the arrow. But when you have, for example, a equation, suppose f of x equal x squared is the famous quadratic function, and why not f of x equal x cubic is the cubic function. Okay, so you apply one thing, it's called a horizontal line test. Okay, let me recall quickly what is the vertical line test we studied before. Before in the chapter 2, we studied vertical line test. And vertical line tests allow me determine if the graph of the function is a function or not. Let me recall quickly. Vertical line test. Vertical line test. Okay, look at that. We have two graphs. X, Y. Suppose that one graph look like that. Another graph look like that. You apply hypothetically vertical line test. It's a vertical line. No? Is the vertical line cross in one point? Yes, it's a function. See the vertical line cross in 2 points or more than no function. This is the idea. This is super easy shortcut to determine if the graph of this equation corresponds with the function. Now the horizontal line test is similar, but in this case more sophisticated, because we determine if my function is one-to-one or no. In other words, si es one-to-one, immediately you understand que es invertible. Okay? Suppose x square. X square is a parabola, you know. Parabola like that. Look. This is a function of x square. You know very well. And cubic is like that. Cubic function. Okay, this is x-axis. And this is y-axis. But you apply a horizontal. Horizontal is horizontal line like that. Boom. Boom. In any position. And crossing only one point here, therefore, yes, it's one-to-one. And here, no, it's not one-to-one. Therefore, that function is not invertible, so the inversive do not exist like a function. And in this case, yes, exists like a function. But what Professor just explained at the beginning, okay, the inversive of the square is a square root. Okay, because, for example, to fix it, this situation, suppose I want to manipulate a little bit this function, the parabola, in order to convert to one-to-one. So you introduce restriction. For example, you put f of x equal x squared. Okay, no problem. But you put semicolon here, x greater than or equal to 0. What mean that? Well, this is the restriction of the domain. So the restriction of the domain is, well, only you assume, suppose like a piecewise function, that the function is x squared if x is positive or 0. Otherwise, que es the complementary part, que es cuando es negative, do not exist. Do not exist. Okay, so my graph look like now, like that. X, Y. Well, okay, it's, or no exactly do not, well, you don't, because the restriction of the domain. So basically, my graph is a half of parabola. Look, a half of parabola. This half of parabola, the positive part, because I define the positive part, exists, and the negative part, invisible, do not exist. But when you apply the horizontal line test, pass the test. So this function is inverted. This function under is the same equation under this restriction. In this case, when you declare like that, default, you suppose that the domain is all real number. Because this all real number is not one-to-one. But in this case, no. In this case, you declare this restriction, que is equivalent in interval notation like a bracket, 0, infinity, so only positive value, and this is one-to-one. Yes, one-to-one. Do you understand the idea? Okay, one more thing, theoretical thing, before I start example, is remember, to find the inverse is easy, because, let me explain, let me erase the board. Okay. One more time, I do in this sketch. This is domain, this is range. Okay, yeah, I suppose now, okay, I am doing a relationship, pero one-to-one, pam, 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 pam. Okay, you connecting this is x1, y1. This is x2, y2. And this is x3, y3. And this relation f is one-to-one. It's obvious que es one-to-one, no? You see using your eyes, no mathematical proof, no horizontal line test in this case. But the important thing is que domain of f is this function is equal to the range. So when you are doing the inverse is in opposite direction. This is the inverse. Okay, you can see que you interchange domain and range. Domain of f would be the range of inverse. Because in this direction, when the arrow is black color, this set is domain. A domain is, let me see, is the set that I highlight in blue color. And range is the set that I highlight in yellow color, no? This is the situation. So domain, but when you interchange, domain of f would be the range of the inverse in the opposite direction. And likewise, the range of the inverse is equal domain of inverse. Okay, range of the inverse is equal, okay. Okay, domain of f is equal to the range of inverse. And domain of inverse is equal to the range of direct. So domain, okay, let me see. The range of the inverse is this guy. Oh, no, I did that. Okay, no. Entonces let me erase that part. Es sinónimo to say que in opposite direction, domain, domain of the inverse is the yellow is equal to the range of the original function. Okay, keep in mind this. This is a universal idea that we use in any example. Because basically the only thing we are doing is interchange domain and range. Okay, we can represent like that. X is the element in the domain. Y is the element in the range. Interchange. This is super important idea. Okay, let's go to the example. I bring 3 examples to illustrate very well this idea. Example 1. Example 1 is a function. It's given. The original is x cubed plus 3. Then we have plus 3, no plus 2, plus 3. And we have different 5 questions. 5 questions. Question number 1, so step number 1 is determine if this function is one-to-one or not. Determine if the function is one-to-one. Because the answer is yes. This open the door to find the inverse, because the inverse exists. Otherwise, no, stop. Suppose que es no one-to-one, entonces no, professor, the inverse do not exist, therefore, I finish the problem, no? Well, entonces the only tool that we have to determine si es one-to-one or no is the famous horizontal line test. So I need to have some idea how it look like the graph of this. Well, actually, the graph of this is a family of the cubic function. Okay, you know the cubic function look like that. It's the cubic function. Because the only thing we are doing is a transformation plus 3. Transformation plus 3 represent the horizontal shift 3 units up. That's it. The graph of our original function is similar, it's the same shape of the cubic function, is the base C, but moving 3 up because it's vertical shift. At that point, normally 0, 0, now would be 0, 3. And my curve look like that. This is x cubed plus 3. Entonces es obvio que when you apply the horizontal line test, es obvio que when you apply the horizontal line test, this pass the test because it's a horizontal line crossing only one point. Okay, nice. Therefore, the inverse function, okay, I need to find in the second step, x is. Okay, x is. Everyone follow me? Okay, because in the second step is determine the inverse. Step 2, sorry. And step 2, you determine, find the inverse function. It's easy. Look, let me show you. The key idea is this. Interchange x and y. This is the key idea. I copy my original function, is given. No problem. Okay, I replace f of x for y because you know in the function notation f of x and y is the same. I know that perfectly. And now you apply this idea. And you put x here and y here. Wow, fantastic. In this moment, I have, this is the inverse function. But the inverse function, unfortunately, expressed in implicit. Implicit form. Implicit, remember, is when the y is not isolated. Okay, therefore, I isolate the y in order to express it in explicit form. So you're subtracting 3, look. And you apply cubic root both sides because I need y alone, totally isolated. So the cubic root of x minus 3 is equal to y, que is the new y, que by the way, this is the inverse function equation. So in other words, the inverse function equation is cubic root x minus 3. Okay? That makes sense because remember the idea behind inverse function. The idea behind inverse function is opposite, in opposite direction. And the original equation, the thing we are doing is compute the cubic root and plus 3. And this is completely opposite. Subtracting 3 and find the cubic root. Okay? This is the formula or the equation of the inverse function in this case. But to make sure everything is okay, I check it. Step 3 is checking. How you check it? How you check it? So you checking the equation. Always. How you check the equation? Well, one super fantastic way, one easy way is form a decomposition. Remember, composition is you have the function and you form a decomposition in between the original function and its inverse. Composition is one inside another, right? In that order. And you see now que condos each other, cancel out. And the answer is identity function. Similar to the example, remember the example that I tried to explain before Okay, for example, you have one function that's inverse x minus 10 and x plus 10, no? But when you put each other, when you replace, for example, this expression here is x plus 10 minus 10 is cancel out that part, and this is the identity function. So you will go back. So if you apply one function and you apply its inverse, the answer is identity function. So we are doing nothing. But in this case, it's no complicated, but it's more complicated, you know. Okay, let me try. Let me try in this order. Suppose that the first function is inverse, is this. Let me use another color. Okay, red color. The inverse function you put inside here, inside this. So you replace. No x cubed anymore. No. It's parentheses, cubic root, x minus 3, raised to the cubic power. This 3 is this 3 plus 3. Do you understand what you're doing? Or no? This is clear or no? So basically, I put together, bro, the inverse function inside the original function. No? And you know, que cubic power and cubic root cancel out, stay entonces alive, x minus 3 plus 3 is cancel out again, is x, identity. This function is called identity function, because it's a function que the x value and the y value is the same. Likewise, si I try in opposite direction, look. Let me use in green color. This plugging it here. Now, we have cubic root. No x anymore. No, it's x cubic plus 3 minus 3. A similar situation happened. Look, this 3 is cancelled. Stay cubic root of x cubic, and the answer again is identity. And you prove officially, mathematically, that this function undoes each other. Therefore, I am super sure that the answer is correct. Okay, remember we have 5 steps. This is a step 3, que is a checking. So step 1 was the proof, que es 1-to-1. Okay, so open the door. Exist the function. The step 2 is the most important step. Is in the step that you find the inverse function, and the step 3 is the checking. Put together this equation and undoes each other. Step 3 is super easy. Step 4, sorry, is super easy. Is determine the relationship between domain and range of the function and its inverse. Okay, this is the original function, f of x. This is the inverse function, and we have domain, and we have range. Let me use a table. Okay. The original function is x cubed plus 3, and the inverse function is cubic root x minus 3. Well, we have no restriction. Remember how you determine domain in the chapter 2. In the chapter 2, the supposition, the assumptions is that the domain is all real number except the restriction. And the restriction we have only when the function contains division, que es illegal division by 0, or square root. Cubic root, no. Cubic root is nice. Cubic root, the domain of the cubic root is all real number. Okay, pero step by step. Entonces now, using this idea, domain of the original is all real number. No restriction, no problema. And it's exactly the same, the range of the inverse. So you copy and paste. This and this is the same, 100%. And the domain of this is also a real number because si es square root, no. Don't allow a negative number inside. Pero si es cubic root, yes. Es negative 3, no? Cubic root negative 27 is negative 3 because negative 3 times negative 3 times negative 3 times is negative 27. Entonces, es a real number que es exactly the same, the range of the inverse. Let's do it in that way to see more clear. In this case, 4 sets are all real numbers. Not necessarily the same, always, no? But in this case, okay. And finally, step 5 is do the graph. Do the graph. Do the graph. The graph of what? The graph of both. The graph of the original function and the inverse function. Okay? Let's do it in my paper, and let's do it, why not, in Desmos after. Okay. Let me try here, picture. Oh no. Okay. Okay, there you go. Okay, suppose the graph. Let's do it by hand, and after we use Desmos. The graph of the original function, so we are doing the graph of this. The graph of this. And the graph of this. But we are doing in super easy way. Pay attention. Okay, look. For example, the graph of the original, you want to find, for example, the y-intercept. Se evalúa at 0. When you evaluate at 0, is the point 3, no? Because 0 cubic is 0 plus 3. So that's the point, is 0,3. And this is expecting. Look, 0,3 here, over there. 0,3. Suppose that you select 2 arbitrary and 1 is negative 1. When you evaluate n1, the original function is 4 because 1 cubic is 1 plus 3 is 4. The point is 1,4. 1,4 here, 1,4. And why not negative 1? Because arbitrary, I like 1 and negative 1 because it's easy, no? And negative 1 cubic is negative 1, and negative 1 plus 3 is 2. And the point is negative 1, 2. And this is expecting negative 1, 2 here. The graph look like that. No secret. No secret. This point was, I forgot to write, negative 1, 2. Okay, this is the graph of the origin. F of x. Let's do it now, the graph of the inverse. But an easy way. Look, the graph of the inverse have similar point, but the idea behind the inverse is interchange x and y. Therefore, point by point, the situation that happened is, this is 3,0. Wow, look at that. I interchange x and y, x and y. Now, x is y, in the original, this is x and y. This is 4,1, and this is 2, negative 1. And the inverse. This is n the inverse, and this is n the original. Okay, let's do it quickly, because it's easy. The point is 0,3. Look, I got that 3,0. Instead of 0,3 is 3,0. Is 4,1 here, 4,1. And 2, negative 1. 2, negative 1 is here, approximately, no? Is 2, negative 1. Excellent. Now in blue color, I try to do my best to make a graph of the inverse function. It's not good, but let's see in Desmos now. of the inversive function is, you know, is cubic root. Look at that, this guy. Cubic root x minus 3. All right, so you remember the graph of the cubic root when we studied in the chapter to look like that. But in this case, the thing that we are doing is inside the radical, and the radical behave like a parenthesis, therefore is horizontal shift 3 unit to the right. Exactly like that. Wow, look at that. These graphs are symmetric. We respect the line. We respect the line. We respect the line. Y equal x can represent the identity function. Okay, any graph of the inversive function is symmetric. We respect the line y equal x. As you will be able to do the graph of any function, the inverse is super easy because you interchange x and y point by point, and you get the graph. Let's do a more elegant graph in Desmos to understand more clear everything. Okay, I open Desmos and one script that I create for you. Okay, contain, let me see. Let me know if you see or no Desmos. Do you see Desmos? Do you see? Yes or no? Yes. Okay, I understand. Okay.
Yes, I see the Desmos.
Okay, super. Now you see example one. Example one, boom, look at that. Wow. Example one is, look, I put a original function. Look. I put the cubic root. I put it using fraction exponent. It's equivalent, you know. I put different point. For example, 0.3, 3.0, 1.4, 4.1, negative 1.2, 2, negative 1. And you see how clear and elegant the graph of the any function and its inverse are symmetric with respect the line y equal x can represent the identity function. Do you see clear? Super clear or no? Question? No? Everyone follow me? Yes or no? Answer me. Follow or no? This is confusing, Professor.
Yes.
Yes. And Lance say yes. Okay.
I follow you.
Okay. And the rest? Everyone okay? Do you follow me? Or you are totally lost? Let's move on to the second example. Second example. Okay, second example. Second example is interesting. It's new one. Entonces, bring me new situation. Suppose que I need to example 2, apply again 5 steps. Pero that function is f of x equal x squared, semicolon, x greater than or equal to 0. Entonces, normally the students say, well, professor, what is that? Semicolon, x, this is the restriction. This is a restriction. Entonces, therefore, I understand que this is not the whole parabola. No, it's a half of the parabola. That part, the positive part, the positive branch of the parabola. Therefore, when you apply the horizontal line test, pass the test. Okay? So you include the other branch, no. It's not one-to-one, therefore it's not invertible. Okay, so I did that. Okay, it's invertible, the function is one-to-one, then the inverse exists. I need to find. Okay, this is step 1. I do quickly, of course. Is determine if the function is one-to-one. It's important to understand que si I erase that part, the parabola contains 2 branches, and the function is not one-to-one, it's not invertible. That's it. So the question finished. because we cannot do anything more because it's no one-to-one. Pero no, our example contains the restriction que become like a one-to-one. Okay, now the step 2 is determine the famous inversive function, no? And remember is you replace f of x for y. You interchange x and y. It's the most important moment. X here equal y squared. And this is the inverse and implicit. This is the inversive function expressed in implicit form. Implicit. Implicit is when it's confusing. Implicit is when the y is not isolated. But when you isolate the y, basically you do that, you apply square root both sides. Square root x is equal the new y, and this new y is the inverse function. Well, professor, I don't understand something. Normally, when you apply square root, you put double sign, plus or minus. No, in this case, no. The reason is no, because we have restriction. Remember, we only consider the positive, not the negative. Okay, so the expression for the inversive function is the square root, que is totally expecting. What is the inversive function for the square power? Square root on those opposite operation or inversive operation. Now the checking. The checking is put together in this order or in this order to verify que on those each other. This is the inversive first. So inverse inside. Inverse inside this is like a square root squared. Es obvio que es x. And in opposite direction is this inside this. Is then square root x squared. Again, is identity because you know very well that square root and square power cancel out. In this case, the domain. Okay, let me see here. The function is given, que is x squared, semicolon, x greater than or equal to 0. And the inverse I found, que is square root x, que I have no idea what the domain, but I suspect it's positive number because it's, okay, domain and range. Well, domain is obvious. It's obvious que is this restriction. If you express this restriction in interval notation is bracket 0, infinity. In other words, only positive number. And this is exactly the same of the range of the inverse. However, I know with my knowledge in chapter 2, that the restriction when you have square root is exactly the same. You take the expression inside, is x greater than or equal to 0. It's a coincidence. This and this is the same. Therefore, the domain is bracket 0, infinity, is exactly the same of the range of the original, only positive. Super. And let's do in the graphic now. And doing the 5-step quickly, no? A ver, 1, 2, 3, 4, and 5 is the graph. Well, the graph, let's see in this to see more clear. The graph, okay, you can do by hand or decimal. I prefer decimals. Then was clear. Okay. Okay, let me share the screen. 2 decimals. I suppose you see decimal now. Yes or no? Boom. Example 2. Look at that. Example 2 is. Do you see decimal, right? Answer me, guys. Yes, no. David, tell me. Do you see this or no?
Yeah, I see, Professor. Thank you.
Okay. Look, David. The blue curve represent the parabola. Of course, half of parabola. I put the restriction. This is the way to put the restriction in decimals. Curly bracket, x greater than or equal to 0. This is the identity function, and this is square. And the point, the traditional classical point is 0,0, que by the way is common. 0,0 and 1,1 is common. It's logical because square root 0 is 0 and power 2 or 0 is 0, no? And 1 is exactly the same, but 2 and 4, no. Suppose that x is 2, when you square 4, and opposite direction is square root 4 is 2. Okay. Okay, in this case, both functions have no negative part, and this is clear of the domain. Okay. Let's see one more example. One more example is, let's see what example 3. Example 3 is this. Okay, I want to copy. Fy equal, okay, let's do an example 3 is more interesting and a little bit complicated. I come back to the whiteboard. Come back. Come back. Do you see the whiteboard? Do you see or no?
Yes, we see the whiteboard. Okay. Now it's blank.
Okay. Now example 3. Example 3 is the function is given f of x is equal 1 over x plus 1. And you need to determine everything. So you determine say 1 to 1, determine the function inverse, verification, inverse is okay or no, on those each other, domain and range. And one more thing I want to explain now. Okay, suppose. Well, I have no idea, I am totally lost. However, I remember something in the chapter 2, the inversive function, so the function is 1 over x, look like that. It's the inversive function. And this is similar to this, except okay, we have plus 1. And this plus 1 is not the same as this. It's no plus 1 outside. Therefore, it's no vertical shift, it's horizontal shift. Horizontal shift, so when it's horizontal shift, is in what direction? It's plus, so it's to the left. Okay. This is a reciprocal function. This is reciprocal function. Contain one vertical asymptote here, but let me show you blue color. Vertical asymptote at x equals 0, vertical asymptote, and one horizontal asymptote at y equals 0. Normal, no? Because degree of the expression on the top is 0 because it's a constant, degree of the denominator is 1, it's linear. Entonces especial in which the horizontal asymptote exists at y equals 0. Okay, and the new one we study now is a function f of x equal 1 over x plus 1. X plus 1 belong to the same family of the reciprocal function, but the transformation I saw using my eyes is the horizontal shift. 1 unit to the left because it's plus. Okay, so when you move the red curve, this red curve, you move to the left, well, I can see something like that. Es obvio que the horizontal asymptote stay the same. Because the horizontal asymptote doesn't change. Because the transformation was horizontal shift. In other words, the motion was horizontal and the horizontal asymptote stays the same. However, the vertical no, the vertical move to the -1 because it's to the left. So we have here now the vertical asymptote at x equal -1. This value, by the way, to be undefined. -1 plus 1 is 0 in the denominator, right? That is the reason que es asymptote, vertical asymptote. Okay. I understand, Professor. However, what's going on is 1-to-1 or no? Yes, apply automatically, immediately the horizontal line test. Let's do it. This is horizontal line test, yellow line, crossing only one. Entonces, es 1-to-1. Therefore, the inverse function exists. I guess so. Okay, this is the only way that we have is you are doing the graph, you apply the horizontal line test. See, pass the horizontal line test is because it's invertible function. Well, why not? Okay, in this case, doesn't matter if you have two branches separately. And when you apply the horizontal line test, you apply only one line, horizontal line, crossing only one point, that's it. Okay, so now let's move on to step 2. Just determine the new equation for the inverse. Okay, let's do it. Remember, it's easy. You replace f of x for y. Okay, you interchange x and y. Now we have x here, 1, y plus 1. Entonces, this is inverse. But the only problem is que es implicit. This is inverse function in implicit. Okay, in order to find in explicit, you do some algebra here in order to isolate the y. Let's do it. I propose you cross multiplication like that. Boom, boom. Entonces, x times y plus 1 is equal 1 times 1 que 1. You distribute here, why not? I try to solve for y. So you move x to the other side, xy is equal 1 minus x divided by x both sides. Y alone is equal 1 minus x divided by x. And this is the new y. And this is the inverse function. Conclusion, the inverse function expressed in implicit is this function. We prove que exists, and we prove also que es equal this expression. Okay, I understand a little bit, but I need to verification, see this work or doesn't work. How you verification work or doesn't work? Well, using the composition. Using the composition in both directions. You using the composition F, composition inverse. Que si es okay, give me identity function, or inverse composition F. Let's do it in both directions to make sure that the inverse works. Okay, so now suppose I take this and replace here in the x place. So my function is 1 over something. This box is the box que es x here, the box plus 1, and you replace 1 minus x divided by x. Wow. Something like that. Let me make it so to see more clear. Okay, it's doing algebra now to simplify this thing. This is 1. You find the least common denominator, que es x. Entonces 1 minus x plus x. Because x divided, this is invisible 1, no? X divided by 1 is x times 1 is x. Wow, look at that. This is cancelled out. And stay alive 1 over x. Reciprocal is x. Wow, fantastic. Fantastic. Un dos, each other. The inverse function and the inverse. Okay, in opposite direction. Bueno, okay, let's do it. In opposite direction is this function. Now, inside this x, and why not this x? Okay? Let's say write something like that. Look. Is 1 minus something divided by something. And inside the something, I replace the original function is 1 over x plus 1. This is 1 over x plus 1 and 1 over x plus 1. Poof. Plus 1. Okay, now algebra, manipulation this. Well. And the bottom, nothing. It stays the same. The top, yes. The least common denominator is x plus 1. X plus 1 multiplied by 1 is x plus 1 minus 1. Okay, this minus 1 is this minus 1. Is it cancelled? So we have in the top x over x plus 1. In the bottom, we have 1 over x plus 1. Oh, it's a complex fraction. The complex fraction always, you copy the top part, exactly the same. Time, flip it, the bottom part. Oof, it's obvious. It's obvious that that part cancel out. And the answer is x. Boom, we proof. Okay, now domain and range. Everyone follow me, guy? It's complicated, this complex fraction, no? You know, always is complicated. But this is an intermediate algebra. Okay, now let me put the table to declare the original function. Okay, it's 1 over x plus 1. The inverse function, okay, we found, and verification, everything is okay, is 1 minus x divided by x. Now domain and range. Okay, the domain of this guy. Okay, let me try to write in an easy way, not complicated. Not necessarily interval notation. Because in the self-builder notation, in my opinion, is easy and useful. Look, domain is the all real number except the restriction, and you have restriction because it's division. So you take the expression in the bottom and you enforce it to be 0. So because x is not 0, therefore there is no negative 1. The only bad guy we have in this game is negative 1. So domain is all real number such that x not equal negative 1. Boom. So basically, in negative 1, we have undefined, okay, by the way, is the asset, the vertical asset. And this is exactly the same, the range of the inverse. But the range is the y value such that y no negative 1. Okay? And here, the domain, because domain is always easier to find. So basically, the idea And this chapter 2 was determine domain, always domain. And range is complicated. But in this case, no. In this case, because you know the relationship exists between the inverse and the original and domain and range. The domain for this is obvious, okay, it's all real number except the bad guy, and the bad guy is 0 because 0 in the denominator is undefined, and this is exactly the same of the range of the original. Okay, so y such that y non-0. End the story. Very, very good, very good. It's super easy to determine domain and range in this case. Now the graph look like complicated, very complicated. Well, I did that, but I did one part, only one part. But I want to do everything. Of course, I use in decimals because it look like hard. So in decimals, look. I share the screen to see decimals. Okay. Okay. Let me know if you see this one or not, guys. Okay, test the number. Okay, look. This is the graph. Oof, look like horrible. But no, let's analyze step by step. Suppose only the first part. Okay, not the second part, not the purple color. This no. Okay, this is the graph. Do you see this one? Yes or no? Yes or no? Answer me, please.
Yes, Professor, I see it.
Okay. Okay, this is the graph in red color of the original function. Entonces it's no new to see, wow, we have one vertical asymptote in -1, and we have one horizontal in y0. Super. However, I discovered also using algebra that the inverse look like that. Boom. Okay, it's 1 minus x divided by x. And this contain, contain what? Okay, contain what? Let me delete mentally, quickly, the original and is asymptote. No, only I focus in the inverse, okay, the purple color, and the asymptote, okay, by the way, look, we have the horizontal asymptote at y equal -1 and x equals 0. Okay? Okay, so now I discovered a new thing. The new thing is in the original function and the inversive function, the value of the asymptote is the same, but interchange x and y. This is not new, it's logical, it happened. Okay, let me put together. Together this is the original function, red color. This is the vertical asymptote at -1 and the horizontal y equals 0. And the new function, is the purple color. Look, the horizontal is -1. Exactly the same value, -1 of the vertical and the original. And x equals 0. Exactly the same value of the. And I give you a point. Well, some point. Let me try different point. In both function. Okay. Different point. And the famous line y equal x can represent the identity function, and you see, wow, how the red curve, okay, the graph of the original function, is symmetric with respect to the is inverse, que es the purple color. Wow, I like that. Okay, entonces now, it's logical que happen, pero happen. It's important to emphasize this idea. The vertical asymptote and the original become transforming like a horizontal and the inverse. And the horizontal asymptote and the original transform it to the vertical asymptote and the inverse. Okay? Super good or no? Okay. So you understand very well this part. I want to introduce a little bit, not too much, because almost we have in holiday the new topic, okay, the exponential function. Today we study no in detail. And next time, I promise, okay, recall again that part. Exponential functions. Okay, you need to understand very much this. Exponential functions is a family. And what definition? What definition? What is the definition? An exponential function, guys, look like that. F of x equal a to the x. Now who is a? A is the base. Is the base. The technical name is the base. And the base is no completely arbitrary number. In principle, it's a real number, but not all real number. Real numbers. Sorry, I don't switch it to the whiteboard, no? Sorry. Let me see again. Sorry. Do you see now whiteboard? Okay.
Yes.
The thing I
It's the whiteboard with the graph on the back. It's not the plain whiteboard.
No whiteboard?
No, it's the whiteboard with the graph.
Okay. My question is, do you see whiteboard now or no? You read exponential function? Or
yes.
No? Okay.
A is the base of real numbers.
Okay. A is the base. It's the base. It's the technical name. And it's real number. Bam, bam. But not all real number. It's only the number positive, so the base is totally illegal to be negative. Okay, it's always positive number. And of course, no, another more restriction, no 0 and no 1. Because this is trivial example. Okay, let me explain in detail. It's super easy. Exponential is, suppose a function f of x equal 2 to the x. It's exponential. So the base is 2. The base is 2. This is just example. Maybe another exponential is the base is 5 or 3 or 7. Okay, 5 to the x is exponential. It's important you see the differences. For example, 2 to the x versus x to the second. This is polynomial. This is a power function. And this is exponential. In exponential, the base is a constant number and the variable is located in the exponent. In this case, completely different. The exponent is constant and this is a number. Do you see the difference? Exponential. And exponential increasing faster. Super faster, right? For example, do you see que, you understand que, for example, the pandemia propagate exponentially? Because the pandemia, for example, one guy gets infected, contaminate 3 guys, and also contaminate 3 more guys. And so this kind of propagation is exponential. Let me show you in detail que es exponential. 3. And so on. Okay, suppose this is exponential, but the base is 3. 3 to the x. Suppose x equal 1. Okay, suppose the moment 1. And the moment 1, or the moment 0, sorry. In the moment 0, we have only 1 contaminate because it's 3 to the 0. 3 to the 0. 3 to the 0, any number raised to the 0 power is 1. And the moment 2, the moment 1, sorry, is 3 to the 1. 3 to the 1 power. 3 to the 1 power is 3. O sea, the infected people is 3. And the moment to, suppose que dice 1 day, 2 day, 3 day, is 1, 2, 3, 4, 5, 6, 7, 8, 9. Is 3 to the second power. This is typical exponential function. And the base indicate us like the rate of change, rate of change of the pandemic propagate. Do you understand the idea of the exponential function? It's no polynomial. It's increasing faster, super faster. Okay, so now when we have that kind of exponential in which the base, so when the base is greater than 1, 3, 5, 2, it's a growth exponential. Growth, 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 growth. Es doble, ¿no? Es doble. Grow, grow, yeah, es doble. Es doble. Grow, exponential. And when the base is in between 0 and 1, it's positive, but this fraction is decay. Exponential. What means to be a decay? Decay means decreasing. Decreasing. Do you see the graph after? No, no, no. So basically, the legal value of the base in any exponential function is, look, this is already a number line. Okay, this is 0 in the middle. This is 1. Okay, so now look, if you have the base and this interval, look, it's decay exponential. Example to decay exponential. Well, is suppose f of x equal 1/2 raised to x. Ooh. In this case, guys, the function here is increasing too fast. In this case, when the base is less than 1, the function is decreasing, decreasing, decreasing. That is a reason that the name is decay exponential, and this is growth. Growth is WTH, no? My spelling is correct or no? David?
It looks fine.
Okay. And in this part is growth exponential. And growth means increasing. And decay means decreasing. It's going down, decreasing. Function.
Excuse me, Professor.
Uh-huh.
Years ago, I had a whole course on probability. This looks like the same type of graph.
No, exactly. Yeah, it's a 3 diagram. Yeah, 3 diagram. Like a conditional, yeah. You're right, yeah. You're right. It's a 3 diagram. 3 diagram.
Right, that's it. I couldn't remember the name of it.
Mm-hmm. Okay, guys. So now we spend the rest of the time quickly to do the graph, at least on the one exponential, and that's it for today because we are almost in holiday. Okay, suppose I want to explain in detail the exponential f of x equal to the x. And also, why not? Let's do in the graph of this. So I suppose that the base is 2. It is 2 because it's easy. Don't worry, because I promise that we continue in the next class. And we are doing more exponential when the base is not 2, it's 3, it's 4, it's 5, it's 1/2, it's 0.5, either way. What about it? Okay, so I propose you to understand this, do the table like that. Okay, look. Wow, what happened with my hands? Okay, and the table, I put here the value of the x. I put the value of the y, case 2 to the x. the point x comma y. X comma y. 0 is good, 1 is good, 2 is good, -1 and -2. It's perfect. And you plugging in. For 0, we have y equal 2 to the 0. And 2 to the 0 is 1. Any number or expression raised to the 0 power is 1. Therefore, the point is the point 0, 1. Yeah, I plot that. Look. I plot that. Is 0, 1 is located here. Good. 0, 1 here. Okay. Do you see? Notice que 0, 1 is a universal point. Because any family of the exponential function, regardless the base, passing through the point 0, 1. Because any number not necessary to raise to 0 power is equal 1. So the point is 0, 1. Look, 0, 1. See, I put, for example, in the test base 3, the point is the same, 0, 1. However, no, in 1, no. 1 is y equal 2 to the 1 power gets 2. Therefore, the point is 1, 2. I plot that point. I plot 1, 2. Boom. This is the point 1, 2. Now, okay. For 2, y equal 2 to the second power, the 4. The point is 2, 4. Nice. 2, 4, 2, 4, 2, 4, 2, 4, 2, 4. Here, over there. 1, 2, 3, 4. Here, over there. 2, 4. And so, suppose I put 3 to say 2 to the third power is 8 and so on, but increasing too fast. You see how fast increasing the exponential function in this direction. It's growth exponential. This arrow indicates also que continue forever. Let's see what happens in the negative value. In the negative value, look, it's important. Y is equal 2 to the -1. And -1, remember, negative exponent means reciprocal. 1/2. And the famous point is -1, half. Let me plot that. -1/2. Half, I suppose, is the middle of this segment here. This point is the point -1, half. Okay. So the exponential continue in that direction. Let's do one more negative. -2 is y equal 2 to the -2, que es 1 over 2 to the second power positive in the denominator, que es 1 over 4, 1/4. The point is -2, 1 over 4. 1 over 4 is the half of the half. Therefore, half of the half is, I suppose, que es this point. So this is -2, 1 over 4. Okay, so you continue plot. Next would be -3, 1 over 8 and so. So this decreasing, pero never touch the x-axis asymptotically. Therefore, any exponential function contains one horizontal asymptote at here, horizontal asymptote at y equals 0. This is universal. Okay? Now let me summarize, and you have the graph. It's clear to see the property for this function. Okay, property. You see, property of the exponential. Or list of the exponential f of x equal to the x. Okay, number one property, what is the domain of this function? All right, the exponential function is nice. As said, you see here, domain is the set of the x value in which the function is defined. It's defined. We can find always y value. This is all real number, no restriction, nice function. Domain. Number two, range. Bueno, range, well, range is a little bit more complicated because we have no exponential in the negative part. Here, no exponential. It's only in the positive part. Remember, the range is the y value in which the function has value is defined. So it's only in from 0 to infinity, but do not include 0 because the curve is asymptotically and never touch the x-axis. Never 0. Okay? This function is increasing. The third property, property number 3. The function is increasing. How do you know that? Remember, increasing is, remember when you want to prove somehow that the function is increasing, you believe that the function look like a roller coaster, the roller coaster car travel always from left to right, and the car, the height increasing, so it's increasing, goes up. So it's increasing function. It's increasing function. Okay, increasing function. And it's obvious that the function is neither non-symmetric, 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 non-symmetric because it's no, when you make a reflection, it's different, no symmetric, it's neither. Okay, another important, super important property is any exponential, the graph is have always horizontal asymptote at y equals 0. Therefore, guys, in the test number 4, the first question is, do the graph of the exponential. I don't know if it's base 2, base 3, base 5, base 1/2, 1/3, arbitrary value. One important part of the graph is the asymptote. Because you are doing the graph and you forgot the asymptote, no full credit for you, right? Super important point. The 6 is a super important point. The super important point is the universal point, 0,1, comma, 1,2. 1,2 gets this point. So the universal gets this point, 1,2 gets this point, and -1,5 gets this point. 3 points is enough. 3 points and the horizontal asymptote is enough to describe perfectly the exponential function graph. However, in general, this is the most important thing now. Listen to me. I finish with this example and that's it. Look, in general, we plot always the universal point. Okay, it's always 0,1. Si the base is not 2, es A, I call, entonces 1,A, and -1, the reciprocal of A. Okay, this is in general. Let's see quickly, and that's it. In the one example, suppose in the test. Suppose in the test, I am the bad guy. Yeah, we do the graph of this exponential function, f of x equal 5 to the x. Well, I see the base is 5. Now, I try to do my best. I remember that the professor said, okay, we have 3 points. This is the typical, let me call typical points. I plot immediately the universal, here is 0,1, this guy. And when the base is 5, this point is the point 1,5, because base A is 5. So it's 1 here, 5, 2, 3, 4, and 5. This point is the point 1,5. And the second point is -1, 1/5, 1/5, because the base is 5. And 1/5, you know, is you take that segment, divide by 5 in 5 portions, using my imagination is here. And this point is the point -1, 1/5. Okay, and that's it. No, we are doing, you connecting this point by the curve. This is approximately. And don't forget, please, the famous horizontal asymptote that any exponential function has. Okay, you put horizontal asymptote at y equals 0. End the story. Entonces now, after the sum giving, we continue doing exponential. And not always when this exponential growth, see exponential decay also, right? Okay, guys, I suppose it's enough for today. The only thing I want to wish happy Thanksgiving for everyone. Okay? Stop recording.